In our last video, we had ended with these formulas here. And so let's explore those a little bit further. What we have here in the numerator is the product of each x value and the height of the function over that x value. So we count x values more where the height is taller. This we will call the first moment along the x-axis. From here on out, I'll probably just call that the first moment. So the numerator is the first moment. And that would also be true if we're looking at the integral. That is just, we break the region down into an infinite number of x values, and we look at the height of the function above each x value. So the x values with more height count more. The denominator in each case is simply the area under the curve. It's just the, so this would be the area of the regions, and this would be, the total area under the curve. Better yet, saying between the curve and the x-axis. So this is the total area. We usually say under the curve, but we really mean between the curve and the x-axis. So if we take the first moment along the x-axis and we divide it by the area under the curve, we will in fact get the average x value. And if we were considering this as an object that has some mass to it, the average x would be the same as saying that we are looking at the center of mass. Okay, so moving along, let's apply this to a calculation for this region. So here we have the region that we had before, and let me pull up a blue pen here. So we know that the function is that the, sorry about that, y equals the square root of x is our function. So in order to find the x center of mass, we're going to need to use our formula that x, I'll call it center of mass this time, is equal to the integral of, in this case, it looks like we're going from, well, I'll just write it out, a to b of f of x dx. Oops, I left out. This is the first moment, so I need to add that it's x times f of x dx all over the area. Should be the integral from a to b of f of x dx. Okay. Now, for convenience, if we're trying to write this integral, the best thing that we can do is start with the denominator. So I would say, step one, let's figure out the area integral. So the area integral would be the integral. In this case, we're clearly going from 0 to 4. The area is going to be easy to compute in this case. It's simply the square root of x with respect to x. So this would end up giving us the area. We won't go into the details of computing that right now. You could compute this area relatively easily using the fundamental theorem of calculus. In a few moments, we'll just use our calculator to get a value for that. The second step that you want to perform is finding the first moment. And once you have an integral for the area, it's quite easy to make an integral for the first moment. All you need to do is add one extra factor of x. So this will be x times the square root of x, or if you prefer, x to the 3/2 power. So that's what the first moment will be. The third step is simply to take those two answers and to get the x value of the center of mass by taking the numerator, which would be the first moment, and dividing that by the denominator, which is the area. So I'm going to pause the video and do the calculations. You can just, on your calculator, directly enter numerical integral and get the values, and I'm going to do that right now. So I've added in the values that I just computed on my calculator. Let me just make a quick note. When you're using a TI-84, you can take the math key, and then go down to select it's number 9 on my calculator. On my calculator, it's select function int. But on some calculators, it might actually show an integral sign. But when I did the integral, I found it very easy if I rewrote it as, it was faster if I just did x, and then I raised it to the 0.5 power. So when I did that, it was faster than trying to enter the fractions 3/2. I'm sorry, this would be for the first one, rather than entering the fraction, the 1/2 power, or taking the square root. Raising it to the 0.5 power was faster. And for the second one, I just made the integrand x raised to the 1.5 power, and that quickly got me the answer. Now, there's just one thing to be careful of as you're doing this. Notice it is the 12.80 that goes in the numerator and the 5.33 that goes in the denominator. It's confusing because we often calculate the 5.33 first, and we calculate the numerator value secondly. So we want to actually go reverse that and make sure we write the first moment as the numerator and the area as the denominator. It's a pretty common error to reverse those two. Now, if we get an answer, it should make sense. So 2.40 is the result of that. And if we go back and look at the area, 2.4 would be right about here. So it kind of makes sense if we put a fulcrum there, since the function is higher out near 4 and lower down here at this end. We need to extend, put the fulcrum closer to the end where the 4 is, so not, a little bit to the right of the middle in order to get this to balance. Now, if we continue onward, we would like to find the y center. So let's go ahead and find the where the y center of mass would be for this object. So let's do the same thing that we did before. We're going to need to find the first moment. So the y center of mass is going to be the integral, I'll just say from c to d, because it's not the same as the a and b values, of y times, and then we're going to need a function in terms of y that we'll be using over the integral from c to d of g of y dy. All right, so we had a few little changes here. First of all, the function that we were working with was y equals the square root of x, but all of our integrating needs to be with respect to y, so we can't use this version of it. What we can say is y squared is equal to x, or x is equal to y squared. So now, as we were doing this integration, we would be actually working with slices that are horizontally aligned. And so I'll just draw a few in. If I take one representative rectangle right here, we can see, we're going to need to find the area, an area element for this. So if I look at that area element, it's going to be, so I'm going to have to calculate my delta A by using a width times a height. Let me just write that over here, width times a height. The width of this thing is going to be the right side minus the left side. And the height will be a delta y value. So if we look at this, every one of the right-hand sides is bumping up to 4 units. So no matter where we are, if we draw rectangles, horizontal rectangles anywhere within the region, the right-hand side would always be over here at x equals 4. The left-hand side, on the other hand, keeps bumping into the curve. So we have to subtract the curve, but since we're using delta y's for the height, we need to rewrite that the left side of the curve is in fact y squared times delta y. So g of y dy is actually going to be replaced by the delta A. So when we go to write our integrals, actually, let's find out the area first. Let's do step 1, which was to get the area. So step 1 is area. To get the area of this region, we're going to want to integrate from y equals 0 up to y equals 2. And we're going to want to use the area element that we just found over here in order to write that area integral. That's going to be 4 minus y squared dy. That would give me the area of the region. And then step 2, we need to convert that into the first moment. And all we have to do to get the first moment is add an extra factor of y. So that would be y times 4 minus y squared dy. And we're going to want to get values for these. And then step 3 will be that we can find that the y center of mass is equal to the first moment over the area. So we'll fill that in just a moment. Let me calculate those on my calculator. So hopefully you noticed right away that the area value that we calculated right here was exactly the area that we had that we were attained when we did this with respect to x using vertical rectangles. So it should be the same because it's exactly the same area. The first moment we calculated is quite different this time. And if we look at the answer, when we take the first moment and divide by the area, we end up with 0.75. So we should always ask, does this make sense? So this is the y center of mass. So if we come back up to our picture, where is 0.75? It's right about here. So this is the balancing line, the horizontal balancing line. And if we combine that with our answer from before, for the x center of mass, which was 2.4, we could put in a line right about here. So the center of mass of this area is right where I put the dot. And so that would be the entire balancing point of the object. So if we were sliding this area, if we cut it out of cardboard and we're sliding it around on a table, as long as that dot is on the table, it will stay, it'll stay on the table. If the dot goes over the edge, the whole object will fall off. So that's how we find the y center of mass. Now, the last thing I want to discuss right here is what if instead of having a flat area, I actually had an object that looked sort of like the area we just dealt with. I'm going to try to draw it three-dimensionally so it would look like it bowed something like that, but it would have a thickness to it. So kind of like a doorstop with a curve to it. So there would be a thickness to this region, and it would extend probably a little bit. If we were looking at it, we would see it kind of extend like that into a third dimension. And if we were going to label these dimensions, this would be our x dimension, this would be our y dimension. And so this new dimension would be the z dimension. Now, because it's uniformly thick in the z dimension, the z center of mass would in fact just be half the thickness. Because of the constant thickness, the x center of mass and the y center of mass would end up being exactly the same as what we just calculated. Same as for area in the, in the xy plane. So there would be no difference if this had some thickness to it or if it was simply an area like we've shown up here. Because the thickness is uniform, the z value of the center of mass is just right in the middle of the object. And so the point that we had here would simply be a three-dimensional point that also was halfway between the two faces of the object in the z direction. I think that wraps up what we're going to talk about in this video.